field model, that is a constant electric field and constant voltage scaling model we will be using, whereas the lateral scaling model we will be not using. And how we are going to use this scaling model is we will be using only two parameters, that is nothing but 1 by alpha and 1 by beta. Yes, can anybody tell me what is the use of this 1 by alpha? For which parameter we will be using this 1 by alpha model scaling factor? Yes, anyone? When we are going to use this 1 by beta and when we are going to use this 1 by alpha? Yes, Jyoti.
Sir, gate capacitance, sir.
No, I'm telling in general, you tell me when I am going to use this 1 by beta and when I am going to use 1 by alpha. So for which parameters 1 by alpha I should use and for which parameter 1 by beta I should use. Yes, anyone?
Sir, when it is proportional, then we will use beta, sir.
When
Uh,
it is?
Proportional,
What do you mean by proportional?
sir.
Yes, Subramanya is here.
Yes, sir.
Yes, Subramanya. When you are going to use this 1 by alpha and when you are going to use this 1 by beta? Hmm.
Linear dimension.
Yes, very good, Dikshit. See, we will be using this 1 by alpha when we are using a linear dimensions, that is nothing but length, width, thickness. So for all these parameters, we will be using a scaling model 1 by alpha, that is linear model. Whereas in the case of voltages, okay, in the case of voltages, we will be using a 1 by beta model we will be using, and in the case of gate oxide thickness, that is nothing but capital D. So in the diagram you can see we have written the gate oxide thickness capital D, right? So for the thickness of the gate oxide we will be using this 1 by beta, and also for the voltages, so when you want to scale down the voltages we will be using this 1 by beta. And one more important thing what you need to remember is for the constant field models and for the constant voltages, so we will be using 1 by for the constant field model we will be using beta is equal to alpha. For the constant field models I'm telling, for the constant field model we will be using beta is equal to alpha, and for the constant voltages we will be using beta is equal to 1. Okay, so with this intentions we studied yesterday several factors. So what is the first factor is gate area. So the gate area Ag is nothing but L into W. So therefore the gate area is nothing but 1 by alpha into 1 by alpha. So therefore the scaling model for gate area is nothing but 1 by alpha square. The next, gate capacitance per unit area. Okay, so the gate capacitance per unit area will be defined by epsilon AX OX divided by capital D. Epsilon OX is nothing but the permittivity of the gate oxide, that is nothing but SiO2, and T is nothing but the gate oxide thickness. Okay, since epsilon is not having any dimension, so therefore we cannot scale down. But whereas in the case of gate oxide thickness we have a capital D. So this capital D you can see it is a gate oxide thickness. So as I said recently, so the gate oxide thickness we will be scaled by beta version, that is nothing but 1 by beta. So therefore the gate capacitance per unit area, that is nothing but C naught will be given by 1 divided by 1 by beta. So you will be getting beta value. Next one, gate capacitance. So what is the gate capacitance? That is nothing but a gate capacitance per unit area into the area. Okay, so the gate capacitance per unit area into total area, if you multiply, then you will be getting a gate capacitance. So the gate capacitance we will be representing in terms of Cg. So Cg is nothing but C naught into L into W. Okay, so therefore your scaling factor will be given as, so we know that C naught, what is just now we wrote, right? C naught is nothing but B naught, beta, L is nothing but 1 by alpha, beta is nothing, W is nothing but 1 by alpha. So beta divided by alpha square. So the gate capacitance is nothing but it has been scaled by a value beta divided by alpha square. The next one is parasitic capacitance. The parasitic capacitance is nothing but AX divided by D. The parasitic capacitance CX is given by AX divided by D, where D is nothing but a depletion width around the source and drain. Okay, so since it is a linear dimension, so we can scale it by 1 by alpha, and AX is the area. So generally area, how you can represent the area, you can represent in terms of L into W. Okay, so L into W means L is nothing but 1 by alpha, W is nothing but 1 by alpha. So what is the area? 1 by alpha square divided by D. So 1 by D is nothing but 1 divided by alpha. So therefore the parasitic capacitance Cx is nothing but 1 by alpha whole divided by 1 by alpha you will be getting. So therefore the parasitic capacitance will be scaled by 1 by alpha. The next one is carrier density in channel. Okay, so the carrier density in channel we will be representing in terms of Q on. So this Q on is nothing but CO into VGS. So we know that CO, what is the value? So the CO is nothing but 1 by beta, and VGS is nothing but it is a voltage, right? So we know that the voltage is scaled by beta. Okay, so it is nothing but, sorry, VGS is scaled by 1 by beta because it is a voltage value, and just now we have calculated that is a C naught. So C naught is nothing but what is that? It is a gate capacitance per unit area is there. So we know that it is beta. So beta into 1 by beta, so you will be getting 1. So therefore the carrier density in channel, that is scaled by a value called as 1. Next, channel resistance. So the channel resistance R on is nothing but L divided by W into 1 divided by Q on into mu. Okay, so mu is nothing but it is a mobility of the charges, and it is assumed to be constant. So for the constant value we will be taking alpha is equal to 1. So L is nothing but 1 by alpha, and W is nothing but 1 by alpha, and this Q on anyway just now we have calculated, right? It is 1. So when you do that, this alpha and alpha will be cancelled it out. So therefore the channel resistance will be 1. So I request all the students, you should remember is that carrier density in channel and channel resistance R on will be having a scaling factor is equal to 1. Okay, once again, carrier density in channel and channel resistance R on will have a scaling factor which is equal to 1. Okay, next one. So the maximum operating frequency will be given by the expression F naught is nothing but W divided by L mu into CO into VDD divided by CG. Okay, so therefore when you substitute all these expressions, so what we have done in the previous case, so you will be getting the maximum operating frequency F naught will be scaled by alpha square divided by beta. And the last one is saturation current, that is IDSS. So for the IDSS, the capacitance, that is a scaling factor, we have calculated as 1 by beta. So similarly, the current density. So current density, how we can calculate? The current density is represented by J is equal to IDSS divided by area. So IDSS just now we have calculated, no? So what is the scaling factor for IDSS? 1 by beta is there, whole divided by area. So we know that area is nothing but 1 by alpha square. So 1 by beta divided by 1 by alpha square, you will be getting alpha square divided by beta you will be getting. Similarly, switching energy per gate. So the switching energy per gate is given by the expression Eg is equal to Cg divided by 2 into VDD whole square. Okay, so we know that CGG is nothing but beta divided by alpha square. Beta divided by alpha square. Just now we have calculated, and VDD is nothing but it is scaled by, since it is a voltage, so it is base scaled by 1 by beta. So 1 by beta whole square, because VDD square is there. So therefore what happens is beta divided by alpha square into 1 divided by beta square. So 1 beta numerator, 1 beta denominator will cancel it out. So therefore the scaling, and that is a scaling factor for switching energy per unit gate area, that is given by Eg is nothing but 1 divided by alpha square into beta. And finally the power dissipation per gate. So the power dissipation per gate, it is composition of a two important component. So what are those important component is, the first one we are going to call it as the static power, that is nothing but PGS. So PGS is called as a static power, which is given by VDD square divided by R on. So the static power we are going to calculate with the formula, that is VDD square divided by R on. And similarly the dynamic power, so the power dissipation per gate, it is a combination of two power, as I said you. One is a static power and one more is a dynamic power. And the static power, we just now wrote it, that is PGS is nothing but VDD square divided by R on. Whereas the dynamic power, so you can see, whereas the dynamic power is given by Eg into F naught. Okay, so we can see when I substitute all this expression, your power dissipations so will be scaled by a factor called as 1 by beta square. Okay, so this is a power dissipation per unit area. Now we need to calculate the power dissipation per that is the previous one per gate. So now we need to calculate the power dissipation per unit area. So the power unit dissipation per unit area is given by, it is nothing but PA is equal to PG divided by AG. Okay, so therefore we can write the power dissipation per unit area is nothing but, so what is the PG, that is scaling factor, it is nothing but 1 by beta square whole divided by, what is the area, area is nothing but always it is 1 by alpha square. So when you substitute that, you will be getting alpha square divided by beta square. See, just now we said the power dissipation per unit area, it is given by that is nothing but Pg divided by Aj. So it is nothing but alpha square divided by beta square. So the last one is power speeds product. So the power speed product, it is given by the expression Pg into Td. So the power speed product Pg into Td. So that is nothing but, so we know that Pg is nothing but beta divided by alpha square and Td is nothing but 1 by beta square. Okay, so if you substitute that, numerator 1 beta and denominator 1 beta will be cancelled it out. So you are left with 1 divided by alpha square in beta square. Okay, so these are the scaling parameters what we are going to use in the case of Vlsi design scaling models. And whatever the scaling model you have considered, it is called as a constant voltage and constant electric field scaling model. Whereas a variable, so one more model I have used, right, that is lateral scaling model, we will be not using in often in the case of fabrication process or in the case of scaling model in the VLSI technology. You see here the scaling effect of combined V and D, the constant E and constant V. So for what are the scaling factors for all, and along with that, what is the scaling factors which will be used for the combined constant V and D and constant E and constant V. Okay, so this is a summarization of all the parameters. Just now we have stopped, right? So all the parameters we have given. So you can see here at the bottom, for the constant electric field, we will be considering beta is equal to alpha, and for the constant voltage field, we will be considering beta is equal to 1. Why I need to study is that because in order to design the system in a systematic manner with cost effective and in a lesser time, then we go for this systematic design process. Okay, so when you want to do any implementation, first you need to make account for the cost and you need to make account of the design and what is the methodology you are going to consider is and what is the manpower you have. Okay, and also what is the time which is available with you and what is the precision you are expecting from your device. So with all these concepts we will go for the system design process. So generally in digital system or in the digital system implementation process, we go for top down approach. So means what, from the design methodology to the fabrication process, so we will go from top to down approach rather than bottom to top approach. Okay, so when you want to design any or when you want to include optimization techniques for your design, then some of the considerations what you need to consider is, so these are the following general considerations you need to include when you want to design the system with the optimum values or with the optimum cost. If you want to do it means, then these are the some of the considerations what you are supposed to consider. So that is nothing but the first and important thing as a customer entity. So you look for the lower cost unit. Okay, so that is one of the general considerations what you are supposed to do when you go for the design procedure. Okay, so in the design of any subsystem or it may be in the main system, the larger quantities are realized through the cooperative ventures such as multi-project chips. That is nothing but the larger quantities we will be measured or it will be depends upon the cooperative ventures, that is nothing but a multi projects chips, or it is also called as a multi product wafers. Okay, so how you design these multi product wafers, so that depends upon the entire cost of your subsystem. So therefore, whatever the design you are going to do it, that is we say it as a multi-product wafer, it has to be a low cost per square millimeter of the silicon. Okay, so this is how you need to consider. The next one is the reliability you need to consider. How reliable your system. So with if it is affected by noise, so how it is reliable, whether it can withstand the high amount of temperature, in which environment you are working your subsystem. So means what? When you design your any system, it should be independent of the environment where it is working for some extent. So therefore, you need to consider the reliability of the system. So generally, for a good system design, there should be a higher reliability. The next one is low power consumption. So this is also one of the important parameters as a customer point of view. We need to design the system which will consume a very less power. So when the system is not in use, or when the system is in idle mode or a silent mode, the power dissipation or the power consumed by the system has to be as minimum as possible. So that has to be taken care as a designer. The next one is better performances. See, whatever we are providing any solutions for any system design we are doing, we are doing for the betterment of the future, or we are going to doing the betterment of the future existing problem. So if we want to design the system in an optimal method, that is one case, but along with that, the optimum system should provide, that is a basic minimum quality of the optimum system designer is that they should provide a better performances. So because this is the only one parameters what we are looking for the optimization. So if you are not getting any optimized or better performances means, then whatever the optimization techniques will not be and no longer will be a significant in the case of design process. The next one is reduce the design or the development period. So whatever the design time you have taken, it has to be also optimum. It's not that you are going to design the entire system. Along with that, the time duration which is taken for us to design this system is to be considered, and how you are going to divide the entire development. So in which time slab, for which time slab you will be given more priority or more time, and for which subsystem or for which period of the design you will be giving a less amount of time. So that has to be calculated priorly in advance. Okay, so when you want to design all these consideration, or when you want to uh, come up with a better system performances or a better system design, there will be some problems always occurs. So what are those problem is? The first one is, if the design is very complex in nature. So if the design is very complex in nature means, then whatever the considerations or whatever the considerations which are necessary for the system, which will increases. Sometimes as a designer, we may miss one or two parameters, and we will start the design. In mid of the design process or at the end moment when we are testing. So when we are testing, we get to know that okay, these are the design parameters we will not take, we have not considered during the initial stages. So because of that, some faults may occur in your subsystem design. So therefore, as the complexity of the system increases, you need to be very cautious about what are the constraints you are having, and what is the methodology you are taking, and how you are going to implement. That has to be studied properly. The next one is the nature of architecture. So what type of architecture you are going to feed? There are different types of architectures are there. So among these different types of architecture, so which architecture it will suits for your application based upon your requirement, you need to understand properly. And the last one is testability. So the end user will be the customer. Obviously, the customer has to be satisfaction. So whatever the parameters which are there for the satisfaction from the point of customer, so all the parameters has to be taken care for the testability of your product. So these are the some of the problems what you need to take care, so that you will be come up with a better design procedure. Okay, so these are the things what you need to understand. So now, so how we can go for the design process? So what is the approaches we can go for this design process has been listed in this slide. So you can see here, if the design process, if it is complex, means one of the simple method how we can find a solution for the complex system is, so we need to divide that into smaller component. So that if I divide the given complex problem into smaller divisions means, then analyzing the smaller component, it will be very easy, whereas rather than taking out the whole projects at a time. So therefore, one of the simple method for the better design process, especially for the complex process, is that we need to divide the complex functions into less complex functions, or we call it as a less complex sub functions, so that we can carefully observe what actually it is happening, and how the output we are getting, and how what are the analysis we can be doing for this subsystem, which will be very good in the case of division of the complex function into smaller method. Okay, so these are the design procedures what we are going to consider. So now, so what are the different approaches are there? So when you want to design, then what are the different approaches are there we need to study? So the different approaches are listed over here. So the first approach, what we are going to call it as the design requirements and the specifications. So that is the first requirement. So how we go for the design? Okay, I have one problem, and for that problem I want to give a solution. So if you want to give a solution means, first you need to take the design requirements. So what is the customer is expecting? Okay, and what are the constraints he is putting, and what are the specifications he want to doing? So let's say you want to have an elevator. You want to design an elevator for your home appliance, for your home. Okay, so when you want to design the elevator for your home, then you need to think, so what is the area which is given for the elevator, and how many number of passengers, let's say how many number of that is a family member they can go for the elevator, and what is the height of the elevator we need to design, what is the power requirements, or what is the power which is available at the home we need to design, we need to consider. So means what, the first step in a design process approach has to be the design requirements and collecting the specifications and requirements from the user. The next one is the logic circuits, or we call it as a logic symbols. Okay, so once you ready with the problem, next what we should do is we should transform that problem into electrical circuits. Okay, so these electrical circuits should provide me the that is a behavioral model of the problem has to be come up with a circuit, and that process we are going to call it as a circuit design process, or also it is called as a logic symbol. So once you design with a logic symbol, the next one is we go for a stick diagram. So we know, right? So before we go for the mask level, it is necessary for us to write on the layered architecture of the circuit. So we are going to use a stick diagram along with the lambda based design rules. So we will be using this lambda based design rules and the stick diagram. With the help of the stick diagram, we can able to create the mask layouts. Okay, so once the mask layout has been defined, then we go for an architectural, that is we will go for architectural block. So once this architecture block has been defined, and the final and the last function of the design process, or the approach, what we are going to call it as a floor planning. So the in the floor planning we will be placing, so in which block which component has to be placed, and where the power system has to be operating, where the wiring has to be taken care. So all those details we will be studying in the floor planning method. Okay, so these are the several approaches what you need to consider when you want to do the design procedure. Okay, so the in order to understand how we go for the arrangements or a design process, so one of the simple example what they have given you, just 2 minutes I will take down this, I will finish off this diagram. So one simple design process for the implementation what they have considered is, so the design of microcontroller, that is microprocessor they have taken. So in the design of microprocessor, so you can see here, so what are the basic component you require in order to design the microprocessor. So this is the diagram which suggests that is the basic components which is required, the basic component which is required for you to design a simple microprocessor has been listed over here. So what are the components you require is, you require a memory unit, and you require a unit, that is nothing but arithmetic logic unit, and you require a control unit, and you require a IO input unit. And you know, right, why we are using this address bus and control bus, especially in the case of in your subject, that is a DSDV. So in the DSDB, if you remember, we have a data path and control path. Write down the VHDL code and Verilog code for the data path and control path. So when one example is there in the DSDB, that is nothing but finding the multiplication of two complex number using that control path and data path. So this control path, what is this is, it will provide the coordination among all the unit. And you can see here we will be having a two address bus. One is the thing, but the data bus is to carry the information from one entity to another entity, and the address bus is to specifically load the information over the memories, and to access the content of the memory we will be using this address bus. Along with this data bus and control bus, that is address bus, we will be using a control bus. So with the use of control bus, so if some entity or some events happens means, then we need to coordinate, and we need to control the some of the input and output devices. So in order to control and in order to provide some signaling informations, we will be using this control bus, and we will be having an input and output section. So with the use of this input and output sections, we can able to display the information, or we can able to collect the information from the user. Okay, so this is the basic diagram of the processor, that is a microprocessor architecture. Okay, so we have a, you can see we have a data path and control path. That is in the data path, whatever the information, it has to be conveyed from one entity to another entity. So you can see here all the entities are connected to address bus and control bus. Why? Because the data path, you can see the memory can be goes out of the memory, and the memory can be written or read from the memory. So therefore for the data bus we have a bidirectional diagram, whereas in the case of address bus, some we require a bidirectional and some require a unidirectional. So based upon the operation of the control unit and based upon the operation of the each entity of the block, we will be writing the arrow marks. So you can see, carefully observe the arrow mark from the control from the control unit. For the control bus, to bidirectional arrow mark is there, because we want to control the control bus. Along with that, we need to get some information from the control bus. So therefore it is having a bidirectional arrow mark. And you can see here for the memory and ALU unit in the data bus, again it is having a bidirectional, because the memory will the data will be moved to and fro from the ALU register and from the memory, and also for the input and output, for display and for taking the input from the user.